Hello, you're welcome back. All right, so I said in this video we're going to be looking at the relationship between alpha and beta. Okay, already we know that alpha is the DC transfer ratio of common base transistor configuration. Okay, so we okay already know that alpha is equal to for a common base configuration. Okay, is equal to the collector current all over the um collector current all over the emitter current. We know that already. Then, of course, beta is the DC transfer characteristics of a common emitter configuration, which also goes as IC, then all over IB. Okay, so I like atomizing my equation. I call this equation 1. I call this equation 2. Okay, so for me to establish relationship between alpha and beta, I have to divide equation 1. I have to divide the two equations. Okay, divide equation 1 by equation 2. So I'm invariably I'm going to divide alpha divided by beta. So which is going to be equal to IC, okay, all over IE, then divided by beta, which of course we know is IC all over IB. Okay, so if that being the case, you know what happens in fraction. Okay, if you wanna divide this fraction at the right hand side, I have to convert the division sign to multiplication sign. Then I have to invert the divide. So this is going to be IC all over IE, right? Okay, then of course, change this to multiplication sign. Then I'll have to invert the divide. So IB comes up. Then of course, IC goes down. So you see IC cancels IC, right? So that way now I can now have my alpha all over beta to be equal to the base current IB, then divided by the emitter current IE. All right. So now for me to be able to establish my relationship, okay. Now don't forget that what we did previously, okay. Or let me state that. Let me state that already. Remember, we said that emitter current, all right, emitter current is equal to base current. Then of course multiply by 1 plus beta. If I can still remember, right? So let's do that. Let's do that into this equation. So I'm going to have alpha all over beta equal to IB, okay? Then divided by IE, which of course is IB bracket open 1 plus beta. Okay, so IB cancels IB, or of course, I have alpha all over beta gonna be equal to 1 all over 1 plus beta. So if I should cross multiply, I can simply have that alpha is equal to, if I should cross multiply, okay, let me do that here. So if I should cross multiply, I can simply have that alpha is equal to beta, right? Of course, I'm cross multiplying. Then divided by 1 plus beta. So I got this relationship is I got it by substituting IE to be equal to um IB bracket open 1 plus beta, right? So this is one relationship. So alpha is equal to beta all over 1 plus beta, right? I can still go the other way around also. I can still get another relationship. Let's look at a situation where still on from this, okay? This relationship that we have here, alpha, okay, all over beta Now we remember we said is okay. We have it to be IB all over IE, right? So now this time around, I'm going to substitute I'm going to substitute for IB this time around. Okay. So I want to substitute for IB. Of course, you know that IB, okay, is equal to IE. Remember that we've done that before. Let me write that down. Okay. We know that IB is equal to IE. Then bracket open 1 minus alpha. Hope you can still remember that, right? So that's exactly what I'm going to do now. So 1 minus alpha, all right? Then divided by IE. So in this case, this cancels this. All right. So I have that alpha all over beta, right? Is equal to 1 minus alpha, of course, divided by 1. So if I cross multiply again, in this case, if I cross multiply again, I will now have that this time around, beta is going to be equal to alpha, okay, divided by 1 minus alpha. Okay, so these are the relationship we are looking at. Okay, so I can still write it down. Okay, so don't if you, in case you don't understand all these steps, just at least be able to get the last step. Okay, the last formula is what I really need, and that's what I'm going to use subsequently. Okay, so I can write that down. I can write that down. Okay, so let me write that down. Alpha is equal to beta divided by 1 plus beta. All right, then beta is equal to alpha divided by 1 minus alpha. Okay, so this is actually what noting. So that way, if you wish, okay, you can cross multiply if you want to. So if you want to, you can actually cross multiply. Okay, so you can actually transform this formula to anything. Okay, if I should cross multiply this, let's look at, let's say this is 1, this is 2. Okay, all right, if I want to cross multiply, let's say 1, I'm going to have that alpha bracket open 1 plus beta is equal to beta, right? Okay, so okay, and basically let me not just transform this formula into, okay, more complicated formula. We definitely use that. So just look at this. This is the relationship that I want to establish. Alpha is equal to beta plus 1 plus beta all over 1 plus alpha, while beta is equal to alpha divided by 1 minus alpha. Okay, so that is the relationship I want to establish. So now let's now go to the last configuration, which of course is common collectors configuration. Okay, common collector. Okay, so that is CC configuration. Okay, of course, in CC configuration, you know what we do. So invariably now I'm gonna be having the transistor, okay, connected this way. But this is the collector, this is the emitter. Okay, so the collector now is common between the emitter, okay, and the base. Of course, you know very well that. Okay, like let me just bias it. Okay, let me just bias it. Anyway, of course, this base, this collector, and this emitter, right? Okay, so now with what I have here, all right, you discover that the collector is actually common. So that means If the collector is common, okay, then my IB base current becomes the input, okay, and my output now is not the emitter current. Unlike what we had before, that the output has always been collector current, but this time around for common collector configuration, the output current is my emitter current. Okay, so let's actually get our transfer ratio. So what transfer ratio are we looking at? So the transfer ratio is going to be the output, which of course is the emitter current, divided by the input, which is the base current. Okay, so now I'm not going to give any symbol alpha beta. I'm not going to give any symbol. Okay, I'm going to establish the this transfer. This is a transfer ratio of a common collector configuration based. I'm going to establish it based on what we have before. Okay, I'm going to establish relationship. So I'm looking at DC transfer ratio of CC. Okay, so now remember very well what we did before. We said that alpha all over alpha divided by please pardon me, IE divided by IB is alpha all over beta. We've done this when we did this. Okay, I can also prove that. Remember, alpha is IC, okay, divided by IE. Then beta is it's gonna be is IC divided by IB. So when you invert it, okay, so you know what happens. Okay, you know what happens. Okay, for alpha, alpha is common for common base. All right, so you know what how actually happens. So that I'm gonna have IC all over times IB all over IC. So this cancels. So I'm gonna have IB all over IE. Okay, so pardon me. So this is at okay, rather the reciprocal of that's gonna be beta. Okay, beta all over alpha. So invariably now the transfer ratio of common collector, okay, IE all over IB is equal to beta all over alpha. Okay, so that way now, let's actually establish the relationship. We already know from what we treated before that beta, okay, beta is equal to alpha divided by 1 minus alpha. Okay, then of course this beta divided by alpha again equal to IE all over IB. Okay, so you know very well that alpha cancels alpha. Alpha cancels alpha. So you now have 1 all over 1 minus alpha equal to IE all over IB. Okay, so if I cross multiply now, I can now establish a relationship. I can simply say that IB is equal to 1 minus alpha equal to IE. IB is equal to 1 minus alpha bracket open multiplied by IE. Alright, so just take this about so I can take this as an equation 1. It's a very important equation. So base current is equal to 1 minus alpha multiplied by emitter current. So please take note of that. We have established the relation, we have proved this equation before, right? We've proved that equation before. Then it can also go the other way around. It can also go the other way around. So in this case, what I'm going to do here is I'm going to substitute for alpha this time around. So I have beta to be equal to alpha. If I substitute for alpha, of course, you know what is it? Alpha is equal to beta divided by 1 plus beta. Okay, it's that's still gonna give me equal to IE all over IB. Okay, so you know very well that this will cancel, and I have 1 all over 1. Okay, so it's going to be a reciprocal, so it will invert. 1 plus IB will come up, so I'm going to have 1 plus IB. Okay, beta, I've already cancelled beta, so I'm left with just 1 plus IB. Okay, it's equal to IE all over IB. So I can still cross multiply again. So this time around, I have IB is equal to 1 plus beta. Okay, then multiply by, please pardon me, IE, not IB, IE is going to be equal to 1 plus beta, then multiply by IB. Okay, so this one is the last relationship. So invariably, when you have a transistor connected in a common collector, the output current, which of course is the emitter current, is going to be equal to, okay, the output current, the emitter current is going to be equal to 1 plus beta, then multiply by the base current. Okay, so we're going to combine all this relationship into practical equations, okay, that we're going to use to solve questions in the next video. Right, see you in the next video. Thank you very much.